Welcome back. We have a question in front of us that reads, an electric heater of resistance 44 ohms is connected to a 220 volt power supply. It is used to heat water of mass 770 grams contained in a copper calorimeter of mass 2400 grams. The initial temperature of the system is 40 degrees Celsius and heating continues until the water begins to boil. The total time taken for the heating process is 3.78 minutes. Given that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin, determine the specific heat capacity of the calorimeter. Solution. Let us try to analyze this problem with a diagram. This is the electric heater that is connected to a 220 volt power supply. The resistance is given as 44 ohms. The electric heater is used to supply heat to the water that is inside the calorimeter. This is the water and this is the calorimeter. The calorimeter and the water will have the same initial temperature, which is 40 degrees Celsius. So the water that was initially at 40 degrees Celsius was heated until it boils. So which means the final temperature that was attained was 100 degrees Celsius, because we know that water boils at 100 degrees Celsius. That means that the final temperature for both the water and the calorimeter was 100 degrees Celsius. The total time it takes for the heater to raise the temperature of the water from 40 degrees Celsius to 100 degrees Celsius was 3.78 minutes. So how do we approach this problem? We always have to ask ourselves, which object or what object is supplying heat, which object or what object is receiving heat. That is, in short, the heat lost by one object will be equal to the heat gained by the other object. So, in other words, we can say that the heater is supplying heat to the water and also to the calorimeter. So, the heat supplied by the heater will be equal to the heat gained by the calorimeter and the heat gained by the water. So, going back to the question, we are told that water has a mass of 770 grams. The mass of the water is going to be 0.77 kilograms. The mass of the calorimeter is 2,400 grams. So that is, the mass of the calorimeter is 2.4 kilograms. We are given in the question that the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. That is, the specific heat capacity of water is 4,200 joules per kilogram per Kelvin. The question is asking us to find the specific heat capacity of the calorimeter. To establish the equation for this problem, we will say the heat supplied by the heater is equal to the heat gain by the calorimeter plus the heat gain by the water. So we can say the quantity of heat supplied by the heater is equal to the quantity of heat gained by the calorimeter plus the quantity of heat gained by the water. How do we find the quantity of heat supplied by the heater? So since the heater uses electricity to supply heat to the water and the calorimeter, we can use the formula for the quantity of heat using voltage, resistance, and time. We know that the quantity of heat is the same as the current times the voltage times the time. So this is equal to QC plus QW. But in this problem, current is not given. So how do we find current? From voltage is equal to current times resistance. By dividing both sides by resistance, current is equal to voltage divided by resistance. So I can use that and substitute it in the place of current. That will be voltage divided by resistance multiplied by voltage multiplied by time. This is equal to QC plus QW. So voltage times voltage will be voltage squared multiplied by time divided by the resistance. This is equal to QC plus QW. That is voltage square multiplied by time divided by resistance is equal to, how do we find the quantity of heat of the calorimeter? That will be the mass of the calorimeter, the specific heat capacity of the calorimeter into the change in temperature. So the change in temperature will be the final temperature minus the initial temperature, plus how do we find the quantity of heat of the water? Is the mass of the water, the specific heat capacity of the water into the final temperature minus the initial temperature. So with this formula, we can be able to find the specific heat capacity of the calorimeter. The voltage is 220 volts, so that will be squared, multiplied by the time is 3.78 minutes. If you change that to seconds, that will be 226.8 seconds, okay? Divide this by the resistance is 44 ohms. This is equal to the mass of the calorimeter is given in the problem as 2.4 kilograms. So that is 2.4 kilograms multiplied by the specific heat capacity of the calorimeter multiplied by the change in temperature will be the final temperature minus the initial temperature. So since the water was heated until it boils, it means that the final temperature is 100 degrees Celsius because pure water boils at 100 degrees Celsius, minus theta 1, which is the initial temperature, is 40 degrees Celsius, plus the mass of the water is 0.77 kilograms. So that is 0.77 kilograms times the specific heat capacity of water is given in the question as 4,200 times the change in temperature will be the final temperature minus the initial temperature. So 220 squared multiplied by 226.8. The answer that you have, if you divide it by 44, you will have 249,480. This is equal to 2.4 times the specific capacity of the copper calorimeter times 100 minus 40 is 60 plus 0.77 times 4,200 is 3,234 multiplied by 100 minus 40 is 60. So we will have 249,480 is equal to 2.4 times 60 is 144 multiplied by the specific heat capacity of the copper calorimeter. So which means we will have 144 cc plus 3,234 multiplied by 60 is 194,040. Collecting like terms, this should be 249,480 minus 194,040. This is equal to 144 cc. 249,480 minus 194,040 is 55,440. This is equal to 144 cc. To find the specific heat capacity of the copper calorimeter, we divide both sides by 144. So this will cancel this. 55,440 divided by 144 is 385. This is equal to cc. So therefore, the specific heat capacity of the copper calorimeter is 385 joules per kilogram per Kelvin. A copper calorimeter of mass 1.2 kilograms contains water at 30 degrees Celsius. An electric heater of resistance 44 ohms connected to a 220 volts power supply is used to raise the temperature of water until it boils at 100 degrees Celsius in 4.9 minutes. After another 22.6 minutes, 660 grams of water has evaporated. Assuming no heat is lost to the surroundings, calculate the mass of the water in the calorimeter before heating, the specific latent heat of vaporization of the steam. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. Specific heat capacity of copper calorimeter is 385 joules per kilogram per Kelvin. Solution. To break down this problem, we have water that is initially at 30 degrees Celsius in a copper calorimeter. An electric heater is used to supply heat energy to the water and of course to the calorimeter until the water boils at 100 degrees Celsius in a time of 4.9 minutes. So as the heating continues for another 22.6 minutes, 660 grams of water has evaporated. We want to know the mass of the water before heating and the specific latent heat of vaporization of the steam. I will begin by drawing the heating curve to explain this problem better. We have temperature in degrees Celsius against time in minutes. Initially, we have water at 30 degrees Celsius. So as the water is heated, it boils. That is, it reaches a temperature of 100 degrees Celsius. And this process, that is raising the temperature of water from 30 degrees Celsius to 100 degrees Celsius lasted for 4.9 minutes. So afterwards, heating continues for another 22.6 minutes. That is, from water at 100 degrees Celsius, water will be converted to steam. Okay, which means we have steam at this point. And this process lasted for 22.6 minutes. That is from this position here way down to this point is 22.6 minutes. To explain this diagram, water is initially at 36 degrees Celsius, and with the supply of heat, it becomes water at 100 degrees Celsius. That is the temperature at which it begins to boil. The total time taken was 4.9 minutes. Then after water has reached its boiling point, heat continues to be supplied to it for another 22.6 minutes. So what happens when water boils? From water at 100 degrees Celsius to steam at 100 degrees Celsius, there will be vaporization. So that is, you will have some quantity of water being escaped into vapor. And if we go back to the question, because water has vaporized, it stated that 660 grams evaporated, which means that was the mass of water that has been lost, okay, at the boiling point. So the question now is, we want to know the initial mass of the water, that is before it reaches its boiling point. We can be able to know that by considering the fact that from 30 degrees Celsius to 100 degrees Celsius, there would be no significant change in mass of the water, okay? So we can use that to determine the initial mass of the water, still using the principle that the heat supplied by the heater will be equal to the heat gain by the calorimeter and the heat gain by the water. Okay, that is for the consideration from 30 degrees Celsius to 100 degrees Celsius. So that is Q of the heater, the quantity of heat supplied by the heater, is equal to the quantity of heat gained by the calorimeter plus the quantity of heat gained by the water. So since electric energy was used, what is the formula for the quantity of heat? We know that it is IVT, okay? But since the current is not given, we've said that if you use current is equal to voltage divided by resistance, and you substitute it here, you will have the quantity of heat is equal to V square T divided by R. So let's write that instead. So the quantity of heat supplied by the heater is V square T divided by R. This is equal to the quantity of heat gained by the calorimeter is going to be the mass of the calorimeter, specific heat capacity of the calorimeter times the change in temperature. The change in temperature will be the final temperature minus the initial temperature plus the quantity of heat supplied by the water is the mass of the water, the specific heat capacity of the water times the change in temperature, which is also going to be theta 2 minus theta 1. So with this formula, we can be able to know the initial mass of the water. Voltage is given as 220. So we square that, multiply by the time taken to heat the water from 30 degrees Celsius to 100 degrees Celsius was 4.9 minutes. If you convert that to seconds by multiplying it by 60, you have 294 seconds. So that is 294 divided by the resistance given in the question is 44 ohms. This is equal to the mass of the calorimeter given in the question is 1.2 kilograms. Multiply by the specific heat capacity of the calorimeter is given in the question as 385 joules per kilogram per Kelvin. That is 385 multiplied by the change in temperature will be the final temperature minus the initial temperature. That is 100 minus 30 plus the mass of the water is what we're trying to find times the specific heat capacity of the water is given as 4,200 joules per kilogram per Kelvin times the change in temperature, which is theta 2 minus theta 1, will be 100 minus 30. So 220 squared multiplied by 294, the answer that you have, if you divide by 44, you have 323,400. This is equal to 1.2 times 385 is 462 multiplied by 100 minus 30 is 70 plus the mass of the water multiplied by 4,200 multiplied by 100 minus 30 is 70. So we'll have 323,400 is equal to 462 times 70 is 32,340 plus mass of the water times 4,200 times 70. So the 4,200 times 70 is 294,000 MW. If we collect like terms, we will have 323,400 minus 32,340 is equal to 294,000 MW. 323,400 minus 32,340 is 291,060. This is equal to 294,000 MW. To find the mass of the water, we will divide both sides by 294,000. So that is, this will cancel this. That is to say, so we can say the mass of the water is equal to 291,060 divided by 294,000. So that gives the mass of the water as 0.99 kilograms. Okay, if you want to convert that to grams by multiplying it by 1000, you will have 990 grams. That was the initial mass of the water before it begins to boil. All right? Although not part of the question, what would be the mass of the water remaining in the calorimeter? Well, 990 grams was the initial mass of the water, and it is stated in the question that 660 grams evaporated. So what was the mass of the water remaining? The answer to that is simple. So always try to remember that the mass of the water, that is the total mass of the water, is equal to the mass of the water remaining in the calorimeter plus the mass of the water that has evaporated. Okay, so if I wanted to find the mass of the water that is remaining, that would have been the total mass of the water is 0.99. This is equal to the mass of the water remaining plus the mass that has evaporated is 660 grams. So that is 0.66 kilograms. So which means the mass of the water remaining is going to be 0.99 minus 0.66. So that is 0.33 kilograms, or simply 330 grams. So which means that was the mass of the water remaining. In some questions, they will be giving you the mass of the water remaining. And always remember that if you need to calculate the specific latent heat of vaporization, you will always need to know the mass of the water that has evaporated. Okay? And this is the second question in this problem. So going back to the diagram, if water at 100 degrees Celsius continue to receive heat, the water vaporizes. So there will be a loss of mass inside the calorimeter. As you understood, from 100 degrees Celsius of water to 100 degrees Celsius of steam, within a period of 22.6 minutes, 660 grams evaporated. So that mass that has evaporated can actually be used to calculate the specific latent heat of vaporization of the steam. So question 2, we know that the quantity of heat that was supplied during vaporization is equal to the mass of the water that has evaporated times the specific latent heat of vaporization. Okay, so that is, we can say, the quantity of heat that was used to vaporize the water is equal to the mass of the water that has evaporated multiplied by the specific latent heat of vaporization. Again, the quantity of heat supplied for the vaporization can be V square T divided by R. So this will be equal to the mass of the water evaporated times the specific latent heat of vaporization. The voltage given is 220, so that will be squared multiplied by the time taken during the period of vaporization was 22.6 minutes. If you convert that to seconds by multiplying it by 60, you'll have 1,356 seconds divided by the resistance is 44 ohms. This is equal to the mass of the water that has evaporated is given in the question as 660 grams. But like I told you, in some questions, they will not give you the mass of the water that has evaporated. Instead, they will give you the mass of the water that has remained in the calorimeter. So how do you find the mass of the water that has evaporated in such circumstances? You will have to subtract the mass of the water that has remained in the calorimeter from the total mass of the water. Okay? But in this problem, since it is given as 660 grams, which is the same as 0.66 kilograms, we will use it directly. So this will be multiplied by the specific latent heat of vaporization. 220 squared multiplied by 1356. The answer that you have, if you divide by 44, you will have 1,491,600. This is equal to 0.66 LV. To find the specific latent heat of vaporization, we will divide both sides by 0.66. So this will cancel this. We can therefore say that the specific latent heat of vaporization is equal to 1,491,600 divided by 0.66. So the specific latent heat of vaporization is 2,260,000 joules per kilogram. If we want to express this in standard forms, we can say 2.26 times 10 to the power 6 joules per kilogram.